Okay. Apparently it's not working. I wanted to use that for another file, but they didn't have it set up ahead of time, so we won't play with it anymore. Okay, so just some announcements. So I have a one-time project meeting this Friday, which will make at NRO, and I won't be able to get back for our normal office hours on Friday, which is usually 11 to 12, so I'm going to push them back to 12 to 1, and it's just for this week only, okay? The library now has the correct edition, the third edition of the textbook on reserve, so if you don't have a textbook yet and need to look at it for the homework problems, you can use the reserve book on at the library. And I've emailed everyone who has specifically asked me for help finding a partner for either the projects or simulation labs. And hopefully I didn't forget anyone. If I did, I apologize, but definitely let me know. And if anybody can stay at the end of class, I'll try to introduce people after class if you haven't already. Try to email each other to meet up. And then for BBA students, there was one student on the list who is a BBA student, and if you're another BBA student looking for help finding a partner, let me know. Okay. So any questions on that? All right. So last time we talked about linear time invariant or linear constant coefficient difference equations, a little bit about solving them, and really we'll use Z transforms and inverse Z transforms for solving these difference equations is the more practical way. So this is the kind of the general linear constant coefficient difference equation we'll see many times throughout the semester, where the output U, so we're thinking of the relationship between U and E more or less as a difference equation that's ultimately we're going to be designing for a compensator, right? So where U is kind of the control output of the controller being input into the plant, and it depends on the error signal, okay? And so we call this an nth order difference equation because U depends on U n times in the past, okay, and it can depend on the input up to m times in the past, time steps in the past. Okay, and we looked at a simple case of looking at approximating integration just using the samples of a continuous time curve, right? And we wrote this effectively as a difference equation, that the approximation of the area under this curve E of tau up through time index k is approximately equal to the approximate area up to time index k minus 1 plus this current area from k minus 1 to k. And we approximated this area over the most recent time interval using a trapezoid. So we can write an explicit formula as a function of these two samples, all right? And then we came up with this recursive formula or first order difference equation. So given the initial condition, okay, in this first order difference equation, we can try to solve it. Okay, so we looked at an especially simple example where E of t is just a straight line, in which case each of these trapezoids is exactly the area. And so this recursive formula is exactly, if you actually recurse, you would get exactly the area at time k. Now, because of the simplicity of this particular example, you could look at the geometry and write out exactly what the absolute formula is. Sometimes, if that's not so easy to do, you can actually take your first order difference equation and just iterate, write out, so U0, 0, then you can compute what U1 is, U2, et cetera, and you might see a pattern, and with the principle of mathematical induction, you can then generalize and prove what the general absolute formula is, okay? Now, unless you have a first order difference equation or simple second order difference equation, typically you won't be able to solve for UK directly in the time domain like here. And so the more practical way, and so this is very analogous to solving differential equations with Laplace transforms, the more practical way is take that difference equation and we're often going to be dealing with higher order, third, fourth, fifth, higher order difference equations. You take the Z transform of that difference equation, you'll have a transform equation, and because of the Z transform properties, which we'll talk about today, you can do algebraic manipulations to isolate what, so in our case, what U of Z is, isolate, get the Z transform, the desired time sequence, and then do an inverse Z transform to find U of K. All right. And so even though that might look like a longer path, in practice, it's the more practical way of solving higher order difference equations. Okay, so the Z transform, you should have seen the Z transform in past classes before. So if you're given a sequence, okay, we're going to call E sub k and say, let's say it's generally a two-sided sequence. The definition of the Z transform of EK is the sum over all k from minus infinity to infinity of EK times Z to the minus k. And as we'll see in a particular example, when you go to compute this infinite sum, it's only going to converge in a certain region in the Z plane. You have to have some constraints on Z in order for this sum to make sense. And the general shape of the region of convergence is an annulus. Now, if you have a causal sequence, which means that EK is 0 for k less than 0, then the shape of that region of convergence is going to be everywhere outside of a disk of radius r0. Okay? And so this is analogous to what you should be very familiar with for Laplace transforms, that if you have a time domain signal, let's say E of t, and you take the Laplace transform of that signal, that Laplace transform integral will only be defined, or will only converge in a certain region of convergence in the S-plane. And the shape of the region of convergence is generally a vertical strip. And if you have a causal time function, then the region of convergence will be everywhere to the right of some vertical line. All right? And so similarly, we'll talk more about stability, but for Laplace transforms, if the region of convergence contains the imaginary axis, then it's a stable signal. For the Z transform, if the region of convergence contains the unit circle, then the sequence is a stable sequence, right? And so what we're ultimately going to see is that we want all poles inside the unit circle, because the region of convergence for a causal sequence, which is mostly what we're going to deal with, is everywhere outside of a disk that has radius equal to the largest pole. Okay, and so if that largest pole is inside the unit circle, then the region of convergence is going to include the unit circle, and it'll be a stable sequence. All right, so let's look at a specific example. And let me see if I can get the pen to come up, and then go back. All right, so here we're going, so this, I've just repeated the definition for the Z transform and the general form of the region of convergence. But now we're going to look at the specific sequence here, and it is going to be a causal sequence. Okay, we're going to use the unit step function, essentially, to make any sequence a causal sequence. So the unit step function is defined as 1 of k. It's equal to 1 for k greater than or equal to 0, and 0 otherwise. And so if we have a sequence r to the k, we multiply it by 1 of k, then this is a causal sequence. So it's 0 for all k less than 0, and then for k greater than or equal to 0, it's kind of this exponential sequence. If r is greater than 1 or has magnitude greater than 1, it'll be a growing sequence. If r has magnitude equal to 1, then the magnitude will remain constant for all k. If r has magnitude less than 1, it's a decaying sequence. All right? So the Z transform, by definition, is we take E of k, this, I'm going to plug it in for E of k in this infinite sum. So we just plug that in here, times E to the minus k, sum over all k. Now, since this is causal, right, 1 of k is 0 for all k negative. So that means that for all k negative, this is 0. So we can simplify the sum down to the sum over k from 0 to infinity. And then from k from 0 to infinity, 1 of k is always equal to 1. So we replace that. So then we just have r to the k, z to the minus k. All right, so then we can write this as the sum over non-negative k, r times z inverse to the k. All right? So now let's call this A. All right, so then, let me go over here so we can see both. So now we have the sum of A to the k, k going from 0 to infinity. And what does that equal to? Or when does the sum make sense? It converges when the absolute value of A is less than or equal to 1. Right? So we need A to be less than or equal to 1. And what is it when A has magnitude less than 1? It's equal to 1 over 1 minus A. Exactly. Right? And so in our particular case, A is equal to RZ inverse. Right? So that means in our case, we need RZ inverse to be less than 1. And equivalently, this means that magnitude of R over magnitude of Z has to be less than 1. Or equivalently, the magnitude of Z has to be greater than or equal to the magnitude of R. Right? And substituting A equals to RZ inverse, back in here we have 1 over 1 minus RZ inverse, and multiplying by Z over Z, we get Z over Z minus R. Okay, so this is the Z transform corresponding to that time domain, discrete time sequence. Okay? All right. And so here, right, the region of convergence is everywhere outside of a disk, centered around the origin of radius R. So let me do that a little better. Right, so the disk centered approximately, it's not much better, but all right, a radius magnitude R, and it's everywhere outside of there. Okay? And so if we look at a few examples, which I left, so I posted up on D2L, it's a one-page sheet on useful summations. This I prepared originally for another class, but I find it that many of the sums come up in many classes. And so this one is here. There are a few other geometric sequences. I also have the Taylor series expansion of that e to the x that we looked at last time. All right. All right, so if we look at a few examples, right, let's look at first case where R is less than 1. So let's look at, say, R is equal to half, right? And you change color so we can see the difference. Okay, so then EK, when equal to R to the K times 1 of K, when R is equal to 1/2, right, it's going to be 0 for K less than or equal to 0. It's going to be equal to 1 at K is equal to 0, because R to the 0 for any R is equal to 1. And it'll be equal to half and a quarter, 1/8. You can see it will converge, right? Now, so this is what you might call a stable sequence. And in this case, right, we have Z over Z minus 1/2. And the definition of zeros and poles is similar to what you should be familiar with for Laplace transforms. Right? When the numerator is equal to 0, that's all the z's where the numerator is equal to 0 are zeros of the transform. So there's a 0 at z is equal to 0. And whenever all the z's where the denominator is equal to 0 are the poles of the transform. So there's a pole at z is equal to half. Right, in this case, right, so the magnitude of R is equal to half. the region of convergence is everywhere outside of that. That includes the unit circle, and it does correspond with a stable signal. Okay? Now if we look at R is equal to 1, then again EK is 0 for negative K, and then it's equal to 1 for all non-negative K. So this, if you will, the signal doesn't decay, it doesn't grow, it might be called marginally stable. All right, so here now we have Z over Z minus 1. There's still a 0 at the origin. Now the pole is at Z is equal to 1, right on the unit circle. Right, so the region of convergence now is everywhere outside the unit circle. The unit circle is on the boundary of that region of convergence. So not inside the region of convergence. It's not strictly stable. It's what we might call marginally stable. All right? And now let's look at some R greater than 1. Let's look at R is equal to 2. All right? So again, it's 0 for K negative, right, since it's a causal signal, and then it'll be 1 here, and then 2 there, and then 4, so maybe, so we have 1, 2, 4, 8. You can see it'll quickly diverge, right, so it's unstable. Here, the Z transform is Z over Z minus 2. The 0 is still at the origin. And now we have a pole out here at Z is equal to 2. And so the region of convergence here is everywhere outside of a circle of radius 2. Okay, so now the unit circle definitely is not at all inside the region of convergence. So it's unstable. All right, and we alluded to this last time. Why is it important to specify the region of convergence? Exactly, because there's a non-causal time domain sequence that has exactly the same Z transform. And so you need to specify the region of convergence to uniquely determine what that time domain sequence is. So it turns out, I'm not going to work it out in detail, but you should work it out as an exercise that if you have, I think it's minus R to the K times 1 of minus K minus 1. That has as its Z transform the same thing, Z over Z minus R. Okay, where now the region of convergence is the opposite. So now its region of convergence is magnitude of Z less than the magnitude of R. Okay, and so this is acausal. It's a left-handed sequence, right? So if I call this, say, E of K, right? Then, right, the 1 of K, we want whenever that argument, just going back, right, when the argument of the unit step function, when this argument is greater than or equal to 0, then this is equal to 1, right? So if minus K minus 1, we need this to be greater than or equal to 0, which means that, bring this to the other side, K has to be less than or equal to minus 1. So only for K less than or equal to minus 1 is E of K non-zero. For all K greater than minus 1, we have E of K is 0. So if you plot this out as a function of K, it's going to be 0 for all positive or all non-negative K. And then it'll be, let's say R is a half. Okay, so then it'll be minus a half here, and then it'll be minus a quarter, minus an eighth. So it's, oh, wrong way. So R, what I plot is R is equal to 2. right? So it can be confusing. So r is equal to 2 because k is negative. So when k is minus 1, we have 2 to the minus 1, which is a half. When k is minus 2, we have 2 to the minus 2, which is a quarter, et cetera. And then you have that minus sign, so it's a negative sequence. All right? Yeah, Usama?
Yeah, I was just wondering, can you provide some motivation of defining the Z transform in the way that it's written over there? Some motivation of defining the Z transform.
Of why it's defined this way? So that's just a convention. That's the definition of the Z transform. I'm not sure what you...
Yeah, but why would you choose this definition?
Over, you're saying like a one-sided. I'm not sure why...
I mean, why would you define it in this way? What really is the significance of defining it in this way?
Okay, so, I mean, that's like asking why is a Laplace transform defined the way it is. So this is basically, it's a transform, okay, and all the transforms, they have their definitions, right? So, like fast Fourier transform, the Fourier transform, for instance. And they're really ways of dissecting a signal so that you can get at certain properties about a signal. So typically, it represents a complex frequency, right? And so when you're looking at a Fourier transform or discrete Fourier transform, so Fourier transform is effectively you're only looking along the j omega axis for a continuous time signal. And discrete Fourier transform, you're only looking along the unit circle. So I don't know. So here, ultimately, we are interested, since we're looking at transient response and things like that, we're interested in the entire z-plane and where are the poles, hopefully all in the unit disk for causal signals or causal systems. And we're interested in where they are inside the unit circle to tell us a little bit about how fast will signal decay or how fast will response to a system decay, things like that. Whereas when you're looking at like a discrete time Fourier transform, you're really only interested in the frequency content. So then you're looking on the unit circle. You're looking at persistent frequencies in the signal. I don't know if that helps, but it's really, it's the definition of the Z transform and happens to be useful, as hopefully you'll see, for analyzing systems and being able to predict responses. Does that help a little bit? Okay. Any other questions? All right. Okay. So, all right, so there are many properties of the Z transform, and there are analogous properties of the Laplace transform, so hopefully these will all be familiar in some way to you. Okay, so we're just going to mention some of the ones we'll use quite often. I think they're more discussed in the book. So the linearity property states that if you have two time domain sequences, little f1 of k, little f2 of k, and they have corresponding Z transforms, cap f1 and cap f2 of z, then the linearity property states that any linear combination of these time domain sequences, and so let's call this g of k, right? So this is some resulting sequence taken as being equal to this linear combination of the original sequences. The Z transform of this new sequence is just the same linear combination of the individual Z transforms. And this is fairly easy to prove, and it's kind of the same process you would apply to prove any property. You invoke the definition of the Z transform, so we want to take the Z transform of this G of k. So you put that function into the definition of the Z transform, right? That time domain sequence, G of k, times Z to the minus k, summed over all k. Right, then you do algebraic manipulations here, and so Z to the minus k, so multiplication is distributive over addition, so you can take the Z to the minus k, put it there, and put it here, and then the infinite sum of one term plus the infinite sum of one term plus another term is equal to the infinite sum of one term plus the infinite sum of the other term, but you're still adding them all up. So then you can separate things out. Then, of course, you can pull the alpha out of this sum since it doesn't depend on k, pull the beta out of this sum since it doesn't depend on k. Then these individual sums, you can see, are by definition cap f1 of z in cap F2 of Z, right? So then that proves that this linearity property holds, okay? And so it's pretty easy to see here, and it's the same kind of idea in proving all the properties. So then you have a convolution property, the convolution of the two time domain sequences. And so here we're looking at the discrete time convolution sum. So when we take these two sequences, convolve them, right, and let's call this G of K, right, you get a resulting sequence. It's a function of K. L gets summed out, right? The Z transform of this sequence is equal to the product of the individual Z transforms. And again, it's the same way for proving it. You would apply the Z transform definition. So you take the sum over K from minus infinity to infinity of this times Z to the minus K. And then you manipulate. So now it's a little more tedious here. The typical thing you would do is you just swap the order of summation between the sum over K and the sum over L. You do change of variables, and you manipulate them so that you can separate out the two sums to have one sum being, by definition, F1 of Z, the other one being F2 of Z. You'll see that you have the product of those, and that's the way you would prove it. Okay, so if you're kind of rusty on this, I encourage you to kind of work through this on your own. It is discussed in the book. Okay, so the main thing here, this property is convolution in one domain corresponds to multiplication in the other domain. And that's one of the reasons why going to the Z transform is, from a practical point of view, the easier way of solving for higher order difference equations, because when you're trying to do time domain solutions, you're going to do a lot of convolution, which is unwieldy. If you go to the Z transform domain, then you're just doing algebraic manipulations. All right? Okay. And then the time shift property, another important property which we'll use quite often. So if f of k has as its Z transform f of Z, then if you shift the original sequence by n, then the Z transform of this sequence is Z to the n f of Z. And again, the way you would prove it is you put this in the definition of the Z transform, do manipulation, change of variables, and you'll see that this falls out. Okay, so if you have f of k, and n, little n is a positive integer, then is this, the original sequence, advanced or delayed? Right, so if you have say you have some time domain sequence, so f of k, right? So let's say whatever it is, like that. So let's say that's f of k. Then if I wanted to plot f of k plus 5, say, do I take these points, shift them to the left, or shift them to the right? So shifting to the left is what we call advancing. Shifting to the right is delaying. I heard both. Advancing. So correct. Yeah, you want to advance it, right? Because if f of 0 was this, right, then f of minus 5 will be that, right? So you're shifting to the left. You're advancing it, right? So then if you want to delay it, so if you have f of k, say, minus 3, then you take that same sequence and you move it to the right. You delay it by 3 time steps. Okay? All right. And then this property assumes a two-sided transform. Okay? And that's how things fall out when you try to prove it. In homework, you're being asked to prove the time shift property, or a time shift property, I think just by 1 unit, for the one-sided Z transform, where this is the definition. Okay, so now, when you do a one-sided Z transform, when you shift, you have to worry about the boundary condition, right, where you don't have to worry about that with a two-sided Z transform. Okay, so that's something you'll have to account for. Right? Any questions? All right. So let's get at maybe asking or looking at why there's this condition that we need to have an integer n. So if G of S is time invariant, okay, is the sample data system in particular, is this system time invariant? So what does time invariance mean? So if G of S is time invariant, what does it mean? So let's say this is, let's say U of t, let's say you just have a step function. So U of t looks like that. And let's say Y of t then is the response, so the step response of some system. Let's say it's a pretty typical step response, might look like that. All right, if it's time invariant, what does that mean? Whoops. If G of S is time invariant, then what does it mean? So say I shift U by some interval. Say ultimately when we look at the sample data system, we'll look at sample periods, but say we shift it by that amount. Okay, what will happen to Y of t? It'll shift by the same amount. So let's see if I can draw this. So, I don't know. Oops. I don't know if I've drawn. So it'll shift by that same amount. All right? Okay, so if G of S is time invariant, now is this? No, it's not. Right? Because the samples of the original U and the original Y looks already flat there, at least in terms of the samples. And then the samples of U, okay, delayed by that half sample period. Now of the Y, it's going to be 0 here, and now it's not the original samples shifted by the same amount, right? Now, under what conditions will this be time invariant? When delays are multiples of sampling periods, right? And so if I shifted the U of t by cap t, then the red curve will be exactly one sample period delayed, and the samples would be identical but delayed by one time period relative to the purple, relative to the first one. Okay, it's similar for integer multiples of sample periods. Okay? All right. Okay, now another property is scaling in the z-plane. So if you have a time domain sequence f of k that has f of z as its z transform, if you take f of k and you multiply by r to the minus k, so you multiply by an exponential sequence, then that z transform, so if this is g of k, right, some new time domain sequence, the z transform of g of k is going to be cap f of r of z, r times z, right? So it's the same z transform, but now evaluated at rz, which means, right, so if, say, P is a pole of f of z, right? So say that you have some, let's say, original poles of f of z there. Then where are the poles of this exponentially scaled sequence going to be? What do you think? It's going to shrink by 1 by r, right? So then now P over R is going to be a pole of f of z. And all those poles, so all the poles of f of z get scaled this way, right? Because if you have, right, so if f of z, you can think of if you have some numerator polynomial over some denominator polynomial, right? So if that denominator polynomial originally, say, z minus p1, z minus p2, you know, we don't really care what's happening in the numerator. So then the poles here are little p1, p2, etc., right? But now, if your z transform is f of rz, so you plug these in here, and so in the denominator, you'll have rz minus p1, rz minus p2. So you can see that this will vanish when z is equal to p1 over r, right? So all the poles get scaled. And so, and then you can also look at this. If we're looking at causal sequences, which is often what we're going to be doing, you want r to be greater than 1, right, for this to be a decaying signal. And so effectively what you're doing is then you're kind of radially projecting the poles when r is greater than 1 towards the origin. And it'll correspond to, if r is greater than 1, correspond to a faster decaying signal. And so the poles being closer to the origin correspond to faster decay. All right? Okay. All right. And then one final property of importance, or final theorem, is called the final value theorem. And there's a corresponding time domain equivalent, continuous time equivalent for Laplace transforms. So for z transforms, the final value theorem states that if f of z converges everywhere outside the unit circle, and all the poles of z minus 1 times f of z are strictly inside the unit circle, then we can compute the final value of a time domain sequence directly from its z transform. Okay, so sometimes we might have, you know, a transfer function for a system, and maybe we then figure out what our output is in terms of a z transform. And to figure out the final value, if these properties hold, then you can compute it directly using that z transform, rather than inverting the z transform and taking the limit. Okay? So what do these conditions mean? Okay, so all poles of z minus 1 times f of z have to be strictly inside the unit circle. So that means that in f of z, the only pole that's not strictly inside the unit circle is a single pole at z is equal to 1, which then gets removed when you take this product. Okay? So that means, you know, if you have your z-plane, you might have a pole, so let's say this is the unit circle. You might have a simple pole at z is equal to 1. All other poles, let's take them in complex conjugate pairs, all the other poles have to be strictly inside the unit circle. Okay, now, the fact that f of z converges for all z outside the unit disk, which means that f of z has to converge for z getting arbitrarily large, right? That means that we have to have a causal sequence, right? Because if you take a look at the definition of the z transform, so in general it's this, and if you look at the terms, right, so let's look at the terms near k is equal to 0. So when k is equal to 0, the term corresponding to that is just f of 0. Then positive k, you have f of 1 z inverse, f of 2 z to the minus 2, etc. Then for k negative, you'll have f of minus 1 times z plus f of minus 2 times z squared, etc. If f of z converges for all z outside the unit circle, that means as z goes to infinity, this sum has to converge. Well, z goes to infinity, these won't converge unless f of minus 1 and f of minus 2 and all f of negative indices are equal to 0. Okay? So all of these must be 0 for k negative, and so really then you just have a one-sided z transform, or you have a one-sided sequence. So it's assuming that f of k then is causal. And so what that means is if you think of f of k, it might have a number of terms, right? And let's say some terms, if they're all kind of those exponential type terms, those all must decay. They must all have poles inside the unit circle. There can be one term that's just kind of some scalar constant times the unit step function, right? That corresponds with a pole at z is equal to 1. And that ultimately then will be the final value of f of k. That's the only term that will persist. Okay? Any questions? All right, so we'll apply these fairly regularly. Okay, now, so we've talked about the definition of the z-transform, a number of its properties, and ultimately, when you get, when you're solving a difference equation, you get down to, so you take a z-transform of the difference equation and do algebraic manipulations, which you'll do by using a lot of the properties of the z-transform. You'll get at your u of z, the z-transform of the desired time domain function. Then you'll need to do an inverse z-transform to get at u of k to solve for the original difference equation. So how do we compute f of k given the z-transform? Right, so we've already said that fundamentally you should specify the region of convergence so that you get a unique answer to that inverse z-transform. In general, this is the two-sided z-transform, but because we're mainly going to be concerned with causal signals and causal systems, we're going to use the one-sided z-transform, which is by definition just truncated. So from k is equal to 0 to infinity, and its region of convergence is everywhere outside of some disk of radius r0, where r0 typically is then, for a causal signal, causal system, is the largest pole of f of z. And so then if the largest pole is inside the unit circle, it will correspond to a stable system or stable signal. Okay, so how do we find the inverse z-transform? So there are many different techniques, a few different techniques. In the end, the most common one that we'll probably use the partial fraction expansion technique. There is a method of long division, and long division can be useful if you're only interested in what the first few values of the time domain sequence is. If you don't care so much about what the entire time domain sequence is, you just want to know what the first few are, then this might be a good method to use. And we almost never use the inverse z-transform integral. Okay, so for long division, what you do is you take your f of z. Okay, so we're going to assume, right, in our inverse z-transform, we're going to assume causal system. So we're going to assume kind of a region of convergence of this form. So we're going to effectively look for a time domain sequence that's causal or right-sided, as they say. All right, so you take your f of z, you write it as a ratio of polynomials in z inverse in order to use the long division technique, and then you perform long division. And then as you're performing long division, essentially you're just going to be backing out in sequence the terms in that z-transform definition. Okay? And so if you're only interested in, say, the first three, this long division technique might be a faster way at getting at f of 0, f of 1, and f of 2, rather than doing the whole partial fraction expansion. Okay, so if we take our example, so we already know what the inverse z-transform is here, but let's use the long division technique, right? So if you're given this as the z-transform, you want to write it as a ratio of polynomials in z inverse. So divide by z in the numerator and denominator to get this. And by definition, e of z, right, is going to be of this form. That's just from the definition of the one-sided z-transform. So what we want to know is what is E0, E1, E2, etc. So what we can do is take our 1 divided by 1 minus RZ inverse. Right, so then we just do long division. So we have 1, and then we multiply 1 minus r z inverse. We subtract, so subtracting this will give us plus r z inverse. So then the next term, because this is a 1, is just going to be r z inverse. We multiply, get r z inverse minus r squared z to the minus 2. Subtract, so these will cancel, and we'll get r squared z to the minus 2. And then you can see that this will be r squared plus z to the r squared times z to the minus 2. And you can continue. So basically then matching the terms, e of 0 is 1, e of 1 must be r, e of 2 is r squared, etc. Right? And of course you can extract out, in this case it's very simple, you can extract out that pattern. You can see that e of k is equal to r to the k for k greater than or equal to 0, or equivalently is just r to the k times 1 of k. As we know from, we've computed the z transform of that sequence to get here before. All right? All right, so long division is useful if you're only interested in a few of those initial terms. Okay, but in general, if you're interested in what the full inverse z transform is, what that full f of k is, it's best to use partial fraction expansion. Okay, because for anything more complicated, it's going to be hard to extract out a pattern. Right? And so the idea of partial fraction expansion is you take some basic discrete time sequences, compute the forward z transform, make a table of these. So then when you're given some new f of z, some higher order transfer function, right, you want to decompose it, that f of z, into partial fractions that each of those terms might be found in your table of z transforms, so then you can back out then what each term will correspond to and figure out then what f of k is. All right, so so the book has a table of z transforms, right? And a comment here is they don't specify region of convergence. They actually don't even specify causality. It just assumes that these are causal sequences. So really this is, k times t times 1 of k. All of these are really times 1 of k. Those are not explicitly stated. It's just sort of assumed these are causal sequences. Okay? All right. And so the one that we have looked at is this one, right, where r is equal to e to the minus a cap t. Right, so then this is r to the k. And so then you have z over z minus r. Okay? All right. So in general, you'll have a transfer function of this form. Okay? And so this is, you can obtain this by taking the z transform of, say, that general differential equation that we've looked at. So we'll see this as a general transfer function of a system or a transform of a signal. So of course, if we want to deal with positive powers of z, we can multiply by z to the n over z to the n. Okay, so for causal proper systems, m will always be less than or equal to n. Okay, so n then will be the larger of the powers, and hence that's why we're multiplying by z to the n over z to the n. And of course then you'll get b naught z to the n plus b1 z to the n minus 1 plus b sub m z to the n minus m over z to the n plus a1 z to the n minus 1 plus our constant term an. All right? So then now this is in terms of positive powers of z. Of course, you can factor out the z to the n minus m. You'll get this form. Oftentimes, we might call this the numerator polynomial b of z and the denominator polynomial a of z. Okay, so it's a ratio of polynomials. And in order to apply the partial fraction expansion, we'll leave b of z as is, but typically we want to factor that denominator polynomial into, say, its poles. So z minus p1, z minus p2, all the way to z minus pn. All right? All right. So now what we want to do is break this up into partial fraction expansion. So we want to take that form, any of these forms, whichever you're most comfortable with, and we would then want to equate this to this form, because each of these terms is now in your z-transform table. In fact, each of these terms here is exactly just that first order exponential sequence that we just looked at, right? And so if you can expand f of z into this form, then you know exactly what the corresponding time domain sequence for each of these is. This will correspond with c1 times p1 to the k, and let's go ahead and explicitly write 1 of k, etc. for all of these. Now c0 is constant. What does that correspond with? It's actually not here. Oh, it's here, right? So it's this one, right? So if you have in the z domain c0, in the time domain you just have a sequence that's equal to c0 at k is equal to 0 and 0 everywhere else. It's what's called the pulse function. Okay? All right. I've lost. All right. Okay. So now let's look at, then the goal is to figure out what are these coefficients. Once you know what c1, c2 through cn, and what c0 are, then you can write down what the time domain sequence is for f of k. All right, so let's look at c0 first. So if you look at left-hand side and right-hand side, right, if I evaluate both sides at z is equal to 0, right, then this will be 0, this will be 0, all of these will be 0. We just have c of 0 left. So that must be equal to f of z evaluated at z is equal to 0. All right, so that's how you would figure out c of 0. And when is c of 0 or c0 when is c0 non-zero? Okay, when the numerator is, okay, so assuming it's a causal system, so we have this, it's C0 will be non-zero only if m is equal to n. But you're correct that if you have non-causal, if m is greater than n, that would also be the case, all right? So, but for causal systems, only when m and n are equal, right? So you can see that here, right? So if you let z be 0, right, if n is greater than m, the numerator is going to be 0. And so f of 0 evaluated 0 is going to give you c0 is equal to 0, right? So only when n is equal to m, then this will be 1, right? And then you evaluate it at z is equal to 0, and so c0 is going to equal to b sub m over a sub n. In that case, it'll be b sub n because they're equal. N and m are equal, right? So basically, you're going to have, this will be equal to b sub n over a sub n, when, m is equal to n. Otherwise, it's equal, that's an n. Otherwise, it's equal to 0, all right? Okay, so now let's look at how we solve for the CI, C1 through Cn. So here, let's just take a look at this case. okay? And the other ones are all identical or similar. So now, if we multiply both sides of this entire equation by z minus p1. So on the left-hand side, we have z minus p1 times f of z. And then on the right-hand side, we'll have c0 times z minus p1. So that's a minus. And then we have plus c1 z, that times z minus p1. Well, actually, let's go ahead and do it. So multiply by z minus p1 over z. So this one will have it over z. And that, then we'll get rid of that. So this term multiplied by z minus p1 over z gives us just c1. And then the next term, the z's will cancel. And we have z minus p1 over z minus p2, and similarly. Okay? So now, if we evaluate both sides at z is equal to p1, on the right-hand side, this will go to 0. This will go to 0, this term. All of these terms will go to 0. You just have c1 left on the right-hand side. On the left-hand side, it doesn't work out to 0 because f of z has in its denominator a factor of z minus p1. So those will cancel out. So you get something non-zero on the left-hand side. Yeah, Topher?
I think I might have missed it when you said it. Where did the 1 over z come from?
So I basically wanted to multiply both sides of the equation by z minus p1 over z.
Oh, okay.
Right? So then this term, basically I want to get at leaving this term with just a c1. This will be of this form, and all the others will be of similar form to those. Okay? All right, so then that's how you would compute what c1 is, which is exactly, of this form. So you compute c2, c3, etc. Okay? So here we're assuming that all the poles are distinct. So p1 is not the same as p2, is not the same as any of the other p's. All right? Now when you have repeated poles, so say you have something of this form. Say p1 is repeated 3 times, and we'll assume all the other ones are distinct, just for simplicity here. Then you would expand things this way. You would have 3 terms that correspond with the p1, right, of this form, right? So one with the z minus p1 cubed in the denominator, one with the z minus p1 squared in the denominator, and one with z minus p1. And then the rest is as before. So you'd compute c4, c5, etc. the same way as before, all right? And here you would compute c3 the same way as before. So if you multiply both sides by z minus p1 cubed over z times f of z, right? So then here you'll have, in the first term, we'll have c1, the z's will cancel, and we'll have z minus p1 squared, and then we'll have c2, the z's will cancel, and we'll have z minus p1, and then we'll have plus c3 plus c4, z's will cancel, we'll have z minus p1 cubed over z minus p4, etc. Okay, and by the same idea, now evaluating both sides at z is equal to p1, this will end up going to 0, this will end up going to 0. All of these other terms have z minus p1 quantity cubed, they'll all go to 0. So the only thing left is c3 on the right-hand side, so c3 is computed this way. Right, and the way to compute c2, now let's take the derivative of this equation before the evaluation of z is equal to p1. Take the derivative of this equation with respect to z. So on the right-hand side, then this will become 0. This will have a 2 times c1 times z minus p1, right? This one, derivative with respect to z, is just going to be c2. That's going to be 0. And then all of these will have z minus p1 squared times something else, right? So all of those, everything else will have the z minus p1 quantity squared. So and then on the left-hand side, we're just saying d dz of this, which I won't rewrite, okay, is equal to that. So now we evaluate both sides at z is equal to p1, and everything will drop out except for c2. So c2 then is equal to this evaluated at z is equal to p1. And that's equal. I don't like when it does that. All right. Whoops. I thought I. All right. So the evaluated at z is equal to p1. All right. So then you can take it one step further. If you took the derivative one more time with respect to z, then on the right-hand side now you have 2c1. And then everything, so these will become 0, and then everything else will have a factor of z minus p1 in it. So now when you evaluate as z is equal to p1, everything drops out and you have a 2c1. So c1 is equal to that second derivative with respect to z of this function evaluated as z is equal to p1 and then divided by that 2. All right? And so I've given sort of the general formula for all of this. So that for C4, C5, computed as before, then C3, computed like this. You take the first derivative with respect to z, evaluate z is equal to p1, that gives you C2. You take the second derivative, evaluate z is equal to p1, and then divide by 2, that gives you your C1. Okay, and in general, if you have repeated roots, say you have a pole that's repeated L times, you can carry out this general idea. So this would be your general formula, that ultimately you're going to have L terms corresponding with that pole that's repeated that many times. And for each of those coefficients, you'd compute it by taking successive derivatives and evaluating. And this 1 over I factorial effectively, is corresponding with that 1/2, right? All right. Any questions? So once you then break it down into these simple forms, right, each of these terms exists in your standard z-transform table, right? So this is the same form as before. This now corresponds to a k times p1 to the k, possibly with some other coefficient, times 1 of k, right? And this is now a k squared times p1 to the k, possibly some other coefficient, times 1 of k. All right? So that these now all exist in your z-transform table. Any questions? All right. Okay, so now there is an inverse z-transform integral, which by definition is this. So you have your f of z, and this is kind of a standard form that you write it in, even though there's a z to the k and a z in the denominator. But this is a contour integral, so you would end up integrating this in the region of convergence. So let's say the region of convergence, say in general, is this annulus. You would do a contour integral, so it's a closed integral, but anywhere in a closed contour, anywhere in the region of convergence to arrive at your f of k. It's pretty complex to do, so we, in practice, rarely ever do it, and we primarily use the partial fraction expansion technique to find the inverse z-transform of f of z. All right? Any questions? Okay, so I think I have a... Oh, so I do have another item that I've posted on D2L. It's a 2-page partial fraction expansion supplement. So here in what we've discussed is we've always, we assume that we're going to factor everything out into its individual poles and then put it into, a form like this. Now, if you have a complex conjugate, if you have a complex pole, for real systems, it will also, the complex conjugate will also be a pole. So they'll always come in complex conjugate pairs. And so if, say, P4 is complex, its complex conjugate will also be a pole. So let's say it's P5. Then the coefficients will end up being complex. that correspond with those, and they'll also be complex conjugate. And so sometimes people don't want to deal with complex numbers in their expansion, and so I put a supplement on the D2L site on if you have a second order factor in the denominator that corresponds with two complex conjugate poles, you might want to expand it where you leave it as a second order factor. And these second order factors also exist in your typical Z-transform table. Then you would deal with only real coefficients. So all the C's here, including C2 and C3, would end up being real. So you try to avoid handling complex numbers. So there's a supplement on how you do that if you want to do it that way. All right? All right. Okay, so I did want to save some time to go over some questions that came up on the homework. So let's see if we can get there. Okay. And it's even further. It's at the end here. So problem 3.1, I think it's problem 4 in the homework. Essentially, so you're given a G of S. It's 1 over S squared. And you're asked to define a D of S to get the closed loop poles to go through a particular points. Okay? So you have your G of S, and you're asked to design a lead compensator, so just a first order lead compensator, so that the closed loop poles go through particular points. Okay, then in part B, so in part A, right, you're just designing that lead compensator, which is of the general form, let's say, some gain times S plus B over S plus A, right? Now, and you design a D of S so you're choosing particular B, particular A, particular K, so that the closed loop poles are at some specified locations, or the dominant poles are at some specified locations. Then in part B, you're asked to use this first order approximation for this delay that we talked about. Right, so let's call it GH. So it's 2 over cap T over S plus 2 over cap T, right? So you're asked to use that, insert it in here, right? So you'll have your GH here, and analyze the system that way. And the idea is exactly what we talked about, that ultimately if you implement your system as a digital controller, because of the zero order hold process, effectively you have a half period delay. Okay, and that's what this is modeling, and we're trying to get at analyzing the system from using continuous time principles, analyzing what the performance of that digital control implementation would be. And a question that I ask in the added problem 3.1c is plot the root locus of the closed loop poles as a function of cap T. And a question then that arose is, well, how do we do that? Right, so ultimately, your closed loop poles of this entire system are governed by 1 plus D of S, GH of S, and times G of S is equal to 0. All right, and you should be familiar with how to manipulate things algebraically so that you can plot versus a different parameter. Okay, so for instance, I'm not going to do that particular problem, but let's say, so of course, say D of S is of this form. So you know how to plot the roots of this equation as a function of K. This is in the standard kind of root locus form. But you should also know how to plot, say I want to plot the roots of this equation as a function of B or as a function of A. You should know how to figure out how to manipulate things into that form. So let's just take B as an example. Suppose I want to plot so let me put K in that case back in here. So I'm fixing K, fixing A, and fixing cap T, and I want to plot the roots of this equation as a function of B. Right? So the way you would do it generally speaking, right? So then you would have 1 plus, so you have S plus B times, and we'll have our K in there, and then let's call everything else, I don't know, let's call it D of S. Okay, so the numerator of everything else is D of S, so I've just factored this. And then the denominator of everything else, of everything together, let's call C of S. All right, so then you have this form. So then, of course, you can multiply things out as C of S plus K D of S times S plus K D of S times B. Right? So then you can write things as, we're going to take all of this, we're going to divide the entire equation by this. Right? So this divided by itself is 1. Then we'll have B, and then K times D of S, and all of that divided by C of S plus K D of S. So now it's in what you consider, so-called this whole thing, H of S. Now it's in standard root locus form. You can plot the roots of this equation as a function of B. All right, so you should be familiar with how to rearrange things. One requirement for the standard root locus techniques is the numerator polynomial has to be of order no greater than the denominator polynomial, the order of the denominator polynomial. So depending on how things work out, you might have to plot as a function of 1 over t if that doesn't work out, right? So that's why I said you want to plot it either as a function of t or as a function of 1 over t. Either way, you'll be able to back out sort of where the poles are as a function of t itself. Right, does that help? Any other questions? And then the other thing I posted on as a news item on D2L is problem 5 refers to example 3.1. It's not referring to problem 3.1. It's referring to example 3.1 in the book. Right? So it's not based on problem 3.1. It's based on example 3.1. Okay, so look inside the chapter for that. All right, any other questions on homework? All right, so we'll go ahead and stop there. And next time, we'll continue on sort of further analysis, on further analysis of discrete time systems, transfer functions, state-space representations, and block diagrams. All right?
Homework's due on Monday?
Homework is due 1 week from today by 5 p.m. Yeah, and so if you wanted to meet other people who also are looking for partners, you can stay behind just a couple of minutes, try to introduce people in person. Right, great. And I do have office hours if people have further questions.